So, good afternoon, everybody. Thanks for coming to my talk on SQL. I'm really happy you're coming, so many of you, because you know SQL is not the quite most popular language at the time. But many new things happen in SQL, and I would like to show them to you, at least some of them, because I don't have the time to show you all of them. So I have picked some of them. And there is one dramatic change that happened in SQL, like 20 years ago. And this is the one I would really like to make you aware of, because SQL is not how you learned it, no matter when you learned it. Chances are you have basically learned something which we called SQL 92. Who has ever heard of this term, SQL 92? Yeah. This is basically what you have learned, and that 92 refers to the year 92 in the previous century. So that's quite a while ago, and it's not the SQL of today anymore. And this is basically what I would like to show you. But before I can show you how it has dramatically evolved in this century, we need to establish some common grounds so that we can say, okay, this was what everybody is supposed to know, and then we need to go on, how is this dramatic change? So out of this many, many years of SQL history, I'm skipping to this magic SQL 92. This is what you probably know what it is, at least roughly. I will repeat it nevertheless, because it's quite important to understand one very central concept, and it's not the relational thing. This is what you know already. The relational idea, what I'm referring up to there, this consists of two components. And the first one is the relational data model. You know that. Who knows the relational data model? Haha, we will see. There is this one term. At that time, in 92, it was referring to, because there are different versions of the definition what the relational data model actually is. And you might still think in the old one, in the oldest one, which is not valid anymore. So that definition was using the concept of atomic types to describe what you can put into a single cell, into the intersection of a column and a row. Atomic types was used at that time. So here you have one of these atoms. And it was used to describe what you can put into the table cells. You see that SQL made one exception already at that time, so it allowed for missing data in form of the null value. So this kind of breaks the relational model, but it was already supported by SQL at that time. So deliberately, at that time, they allowed something which does not fit into the original definition of the relational data model. So this was the first thing, this atomic type idea. And then there is the other idea, the normalization. Who knows what normalization is? So you might have heard of these normalization levels, first normal form, second normal form, and so on. How many do we have? Who knows? 3? 4? 5? 5? Actually, more than 6. So they are numbered from 1 till 6, and then there are a few which don't have numbers, they have just names. So who needs them? Yeah, you get it. But the important thing is actually the first normal form. The first normal form is actually the relation, what a relational model actually is. So the first normal form is the foundation of everything, and everything on top of that, like stacked layers, lasagna code, or whatever you want to refer to it, this is then refinements to get additional benefits for additional, you have to pay something, of course. But I would really like you to ignore this formal definition of normalization. Just think in the sense of the word normalizing the data. Try to store, and this is the original idea, try to store the data in such a way that it is immutable even when the requirement, what you want to do with that data, change. This is the really important idea, because you have some persistent model, and that should be more or less static, as good as it goes. You will, of course, sometimes need to add some more columns to some table, no question, but it should still be independent of what you're going to do with that data, how you process it later on, or even where it comes from, because that is something you don't know. You don't know the requirements of tomorrow. Nobody does. So the idea already at that time was, if we normalize the data in such a way that the schema only considers the true nature of the data itself, but doesn't care about what you want to do with that, then you're actually independent of when the requirements change. Then you can basically implement every single requirement in a convenient way because you have something, a natural form of persistently stored data, which you can then transform for some requirements. So this is the actual idea now in a layman's term idea. So what you know, one of the consequences is that you will end up spreading data over many tables. Okay, that's what you know. And this is where the second half of the relational idea comes into the game. Because working with those many tables is kind of inconvenient, let's put it that way. So therefore, we have these relational operations like join. You know join? Who knows join? Who doesn't know join? I'm sorry, you're wrong in this talk. Yes. Okay, you will still be able to follow. It's all fine. Stay here. Take a coaster. So the key idea, the fact that it is question?
No, I misunderstood the word. I know what a join is.
Yeah, it's okay. Yeah. It's all fine. We are all friends. Okay. Okay, so everybody knows what a join is. Let's tape that. So the idea on this right-hand side of this chart, of this slide, is actually that we need some way to conveniently, on the fly, transform something which is persistent and independent of what you want to do with that to something that is more convenient for whatever processing requirement you're implementing right now. And you're implementing many of them. It's not only one. Sometimes you write a report, sometimes you write a UI, sometimes you do this and that. You don't know what you want to do with that data tomorrow. So if you have a unified data schema persistently and can easily transform it into whatever requirements you need, that would be quite handy. And this is the core idea behind the query language SQL. I shouldn't say query language, because in the title I say it's more than a query language. It's actually a transformation language. This is what SQL is. I will show you a query language later on, and then you will see the difference between a query language and a transformation language. So you see, this was the original idea behind that. So we have this normalization in the layman's idea, just make the data model independent of where the data comes from and what you're going to do with it later on. And then you can, on the fly, dynamically transform using a powerful language. But at that time, in SQL 92, that powerful language was mostly influenced by the relational algebra. And then there was the next standard, SQL 99. It's an ISO standard, also before, 1975, if you're interested in the number. And it was really a big bang. It has changed pretty much everything. This is now the modern SQL I'm talking about. And to give you an impression what it is about, I'm quoting a paper here, which appeared about the time when the standard was released. And just look at the headline there. Great news! The relational data model is dead. Isn't that great? I mean, I could post this today on Reddit or Hacker News and everybody would, whew! Isn't it that way? Like the NoSQL folks, like 10 years ago. They said, oh, relational data model is not so great. Okay, we found out 20 years ago. That's no news. It's written there. So I will show you what it actually means. But first, I would like to give you an impression by two quotes out of this paper. The first one goes, to say that these SQL 99 extensions are mere extended interpretations, important word, extended interpretation of the relational data model is like saying that an intercontinental ballistic missile is merely an extended interpretation of a spear. Yeah, it's kind of similar, those two concepts, you see. But yeah, you can see there's some evolution between, but still it's somehow also different. So the message there is yes, it is on the one hand it's the same, but on the other hand it's so fundamentally extended that we might need another word for it. And the paper was actually suggesting to use the SQL data model instead of relational data model. However, there's another quote. With SQL 99, you can get the best of both worlds, and of course, you can get the worst of both worlds. It's up to the database practitioners, that's us, to do the right thing. So here in this quote, there's basically the message like, oh, you can still do it like before. But now you have more options, more freedom of choice. And it's among us or you to actually choose what is the right tool every single time you're using it. So let's go into the details. What has changed so dramatically? Let's first look on the model side, the relational data model. What has changed there? Extended interpretation. So to quote some smart guys, I'm actually quoting Chris Tate here. He and many other people were thinking about that in the 90s. But I'm quoting him because he wrote a lot about it. So it's easy to quote him because of his books. And there in one of the books he wrote, I was as confused as anyone else. He was confused. Everybody was confused. What were they confused about? And it turns out what they were confused about is this atom. What is it? It describes what you can put into a table cell. But atom is something you cannot split up into smaller parts. But, well, a string, a character string, for example, obviously it can be split. So it's not atomic. So they were just questioning from scientific perspective, like, okay, we know what it is meant, but how could we find a better word which describes what is meant? Because atom is absolutely not what we mean. Because the only atomic thing of information is the bit. And of course, it doesn't make sense to have only one single bit in each table cell. So this is not what's meant. So they were searching for a better definition. And then he writes on, by the early 1990s, I have seen the light. And in his own words, he writes, domains can contain anything. And in our language, it basically means types can be anything. It doesn't need to be atomic. It basically just crossed out that single word of the definition of the first normal form. And on the first normal form is just the basis for the second, the third, and so on. So what they did at the time, they redefined the foundation. And when I imagine this, it looks for me like a Jenga tower of stacked normal forms, and they were fiddling around at the lowest level. And he was replacing something, and everybody knows, no, it will break. And he replaced that, and nothing happened. It turned out that all the definitions of the higher normalization levels are still valid if you remove that atomic requirement. And nowadays, and this is what SQL 99 started to take up, you can put whatever you want in there into each table cell. And you don't break the relational model, you don't break any law, you don't break SQL, it's just fine, go ahead. It has been proved, the battle has been won 20 years ago. So what does it mean? SQL 99 allowed rich data types. And of course, we can still take the old atomic data types, like character strings and dates and integers and all of that. They are still useful, no question. But now we have official support for arrays. Have you ever heard the wording like no repeating groups should be in table cells? Who has heard that? Yes? Mm-hmm. That was in the original definition of Mr. Cott, like 40 years ago. It has been replaced by him own and later on by other ones. It's not a valid definition nowadays anymore. So we have explicit features for arrays in SQL. It goes on, even more scary to be honest. We have nested tables. You can have an entire table in a single table cell, and in those cells again a table if you want to. This is not the way you want to work. So this is not the data model you're looking for. But more useful, composite types. Like you can now create type money, and you can combine there the currency symbol as well as the numeric value of it. And then you can have a single cell that has both of them combined. And if you later on use SQL to do some transformations, you will even enjoy the type safety of SQL. So that's there. So that is on the model side what has changed. On the transformation side, they also found, all this relational algebra, it's quite useful sometimes. And sometimes we would like to have more powerful features which have no equivalent in the relational algebra. So they have basically introduced transformation steps that are in no way influenced or related to the relational algebra anymore. So I'll show you one of them. And the example I would like to show you here, it's about recursive queries. Who is afraid now? Scared? Okay. So you know, like a data model like that, if you want to store a hierarchy, you can basically, one of the ways you can store it is that you basically take a table design where you have an ID, of course, and then you have some other column where you store the parent. And this is basically one of these arrows you have there. And so each of these boxes is one row. And if you want to pick one of those rows, like that one, then it's easy enough if you know the ID. So let's suppose we know the ID, but then the question is, how can you find all the ones beneath that in SQL? So this is the example I would like to show you. And it starts, of course, quite easily. If you know the ID of the root node you want to start with, then you just query that. Let's say that's like 42. Who knows what the question mark is? Prepare bind marker, yes. Who doesn't know what that is? Okay. In case you don't know what that is, this is the prevention of SQL injection. Read about it. So this is basically the bind marker or the placeholder for an actual value. So if you know the ID by value, you can search it. Okay, that's easy enough. But the question is how to proceed, how to find the subtree there. And even SQL92 had some support for that because we have had the union all operator. So we can combine another result set of another query into a single result set in a single query. And here we can do basically search the same value, but not on the ID column, but on the parent column. And this way we can easily find the second level there of these nodes, because now we are searching for all the nodes that point to that parent. So far, so good. But when it comes to SQL92, we have also like a dead end here, game over. We cannot add a third level here. Although we could add union all, another one, you can add as many as you want. The problem is the data model doesn't have a grandparent pointer. And honestly, we don't want to have one. So how can we continue there? And the key idea, which is now enabled with recursive queries in SQL99, is that we need some way to express a search that reprocesses its own output again. So as soon as I found one of these results here, some ID of those two nodes here, I would like to search again on the parent column for those two IDs I have just found. And if I repeat that over and over again, then I will eventually find all the nodes, the entire subtree. And this is exactly what we have a syntax for. And look there, it's not a lot. It's just a few lines there, a few lines there. You don't need to understand the syntax now in detail. The important thing is that we have this indirect self-reference here. So we have down there, we are searching on this pref ID, which is a reference to its own result via this indirection. And if you run this query, if you copy and paste it in your database, it will run and it will immediately find all of those nodes as deep as you want. Just one query and you get one row for each node, everything which is beneath and nothing more. So there is no need to go ping pong between your client and your database. It's just one query you throw at the database and you get back the result you want. So this was defined 20 years ago in the SQL standard, in the international ISO standard. And yeah, the ISO standard is a pile of paper, a big pile of paper. The actual question is which databases implement that. And this is why I have these slides for you. There you can see which database supports it for how long. A selection of 7 major databases. So if you see here, who is using MySQL? Yeah, who is using MySQL 8.0 in production? Okay. Who sees a reason to migrate right now? Okay. So you see, MySQL was pretty much late to that game. Like last year coming with the GA release that supports that kind of query. But that is the concept is very mature. There are mature implementations, as you can see in this chart, and even the MySQL implementation, although it is a rather young one, it's okay. I tested it. It's pretty much okay. So you can basically use it. If you need that, it's there. And it's not a special MySQL thing, and there's no vendor locking or so. It's an international standard. Okay, that was just one feature I have picked out of the SQL99 standard, and I have to rush on to the next one, 2003. And there were also 2 interesting changes. again on the model side and on the transformation side. And as you can see there, XML was a big thing at that time. Who's using XML nowadays? Who's using JSON? So therefore, I will not go into the details of XML here, but the breakthrough there was that for the first time we had non-uniform documents in single columns. That's something which was not even supported with SQL 99, because there, if you had an array, then it was a typed array, like array of int. If you had a monetary type, then it was a monetary type throughout the complete table. Every row in that table has to have the monetary type then. But now we have had document types, if you want to say so, or schemaless, whatever you prefer. So that was the first time that was introduced in SQL. XML at that time, because XML was the hip shit at that time. Later on, we have got JSON support, and this is what I will show you later on. And on the transformation side, we have got window functions. This is the over clause, if you have ever overseen. Who knows what window functions are in SQL? Oh my God. Again, who knows window functions in SQL? Just like 5 maybe. Okay. I have bad news here. Who is having SQL on their CV? Nobody? Nobody MySQL on the CV? Yeah, on the. Do you have it on your resume? So do you claim that you know SQL? Who is claiming to know SQL? Yeah, you see there's something bad coming for you. So if you have SQL on your CV, on your resume, and you don't know window functions, you're basically lying. I'm sorry to tell you. You have to cross it out. I'll wait here. No, but the good news is I will show you so you can put it back on in like 10 minutes. But really, this is such a game changer, the single feature, window functions. It was taken up by even the more modern SQL thingies like Google BigQuery and Impala and Spark SQL and so on, and also by many non-SQL systems. They also support the concept with a different syntax, of course, but the concept is there already. So what is it about? Imagine the query that I see there and the result it returns. And this is basically like transactions, like deposit and withdrawal. So there is a deposit of 10 and another deposit of 20, and then we have a withdrawal of 10 and so on. And what I would like to implement in SQL, in modern SQL, is another column, balance, that tells me what is the balance after each transaction. So when we start with 0, the first one should be 10. If I add another 20, I will have 30. If I take 10 out, it makes 20, and so on. Of course, there were also solutions in SQL 92. You can have subqueries, you can have self-joins. There were many solutions, but they were ugly, slow, error-prone. Yeah. And now we have another solution. Because these window functions, one of the key ideas of the window functions is to be able to use aggregate functions like sum without being forced to do a grouping. This was strictly combined in SQL 92. If you're going to use sum, count, min, max, average, you also have to do some grouping. And this has been lifted. It's gone. This limitation is gone. You can now use aggregate functions without grouping. Then you need, of course, another way to specify which rows you would like to apply the aggregate function on. And this is what we have the over clause for. So here I'm using the sum function, and instead of having a group by at the end, I immediately follow after the sum. It still belongs to the sum function, the over clause. And there I can specify over which rows, hence the name, over which rows I would like to apply this aggregate function. And it starts in a little bit in an odd way, I would say, with an order by clause. That confused me for quite a lot. When I started with that, I was confused about it. If I summarize something, why the heck would I like to order it first? Like 1 plus 2, 2 plus 1. Close enough for my taste. So why are we doing that? And the reason is actually we want to establish a common understanding between me, us, the developer, and the database. Because it's a declarative programming language. And we will soon declare something using the word between. I would like to apply that sum function over the rows between, from there till there. And so that this between makes sense, we need to establish a common understanding of according to which order. So here I'm basically saying, okay, I'm going by ID for the simplicity, and then I can say things like, I would like to apply the sum function on the rows between unbounded preceding, so without limits upwards. And, so this is a pointer to the beginning of that result set, and current row. And this current row is a floating reference. When the database is looking at the very first row, unbounded preceding is the top, current row is also the top, so it only aggregates a single row, which gives you the result of 10. But at the second row, unbounded preceding is still the top, and current row is the second, so now you have a frame of 2 rows, so the result makes 30, and so on, and so on, and so on. There's a question, yes?
Would you keep this for a simple operation, or can you do things like, for example, in event sourcing, aggregation over complex events, where every traversed entry produces some new state?
Yeah, so the question is this just for simple cases or also for event sourcing, like get the current state out of the past? So in that sense, I think you can basically use it for everything. It's really, really powerful. Here it's just the simplest example, but here you can also say in rows between, you can also say things like 3 rows preceding and 3 rows following, and then use the average function, for example, so to have a moving average. There are many, many possibilities. I cannot show all of them here, but it's really countless. There is no limit. The sky is the limit, if you want to say so. But, you know, the SQL standard is just a piece of paper. Can you use that in your database yet? Yeah. Welcome. You can. It took us like 17 years, but now it's there in all the major databases. Is anyone using SQLite in here? So that was the latest database. Oh, quite a few. Are you using it on Android? Oh, I'm sorry. You have to wait 5 more years. At least. Yeah. Okay, so this was window functions, just a teaser. There is really so much power in that. If you want to know more about SQL, this is the place to start. Really, window functions, Google it. I would like to go on to the current standard, straight to the current standard. There were some other standards in between, but I don't like them too much. So let's go to the current standard, 2016. And what we have in there is JSON. Who likes JSON? Ah, great, great, great. So you could, of course, forever store JSON documents in SQL databases, because a JSON document is just a character string. The big difference is now that SQL now has an understanding of what it means. What do these curly brackets mean? What do these square brackets mean? You can now ask questions like, is this a JSON document? And you will get an answer, yes or no. And then you can ask, what type is it? And then you will get the answer array in that example. And then you can ask, how many elements does it have? And you will get 2 in this example. So it has now a semantic understanding. And as I mentioned before, one of the key ideas of SQL from the beginning was transformation between different ways to represent the same data. So you remember the more atomic table design, like the normalization, like we know it from SQL? Wouldn't it be handy if we would have a single function that transforms a JSON document into some more tabular design, and maybe vice versa? That's what we have now. The function is called JSON table. That's the entire query. I will go through it with you. So here we have the name, JSON table. You use it in from clause because it's a table function. It gives you a table as a result. Then we have the almighty question mark again, which is here basically to describe the JSON document itself. So you have to provide it with the data. And the next step is using a so-called SQL JSON path expression. And this is now a query language as opposed to transformation language, a query language. It has the same function like XPath or XQuery has for XML. Who knows XPath, XQuery for XML? It's the same thing just for JSON. If you don't know XPath, XQuery, maybe you know CSS selectors. Who knows CSS selectors? Yeah, CSS selectors for HTML, JSON path for JSON. So it's a language to describe, to pick some elements out of a JSON document. And the syntax I'm using here, the $sign is the root anchor. Then we have the square brackets for an array and the asterisk for all elements. So this JSON path expression will hit the 2 elements I have in there. And that's the reason why the JSON table function will give me 2 rows. Because each of the elements this expression hits will be turned into a row. And in SQL, it's really declaring the result. It's all the time about describing which rows would I like to have, what we just did, and then which columns would we like to have. And you see it already. There's the columns clause, and there you define the names, the types of the columns. And of course, you can again use this path expression to tell it which data to take and put into that column. And that's it. That's the entire query. And it transforms that JSON document into a more tabular design. And you can take care of error handling. You can take defaults if you don't find anything and so on. You can pass date strings because JSON doesn't have a unified timestamp format. So there's some syntax how you can pass that, all of that. Does that sound, look like something useful? Except that this particular example is not so useful, I find, because of this one. I'm putting here a question mark. So I'm providing data from the client, and I'm selecting it back to the client. Is this useful? Oh, sorry. There's the slide broken. Now I need a short interruption, sorry. Wrong slide, wrong slide. Let's try this one. Okay, this is actually the use case. Oh, come on. Once it starts going wrong. Okay, so this is actually the use case, because it's the same like before, except that I've put the insert statement up front. So that means I'm sending a JSON document to the database using a bind parameter. And in the database, it's transformed into a tabular form and directly loaded into a table. A single round trip to the server. And I'm just declaring the mappings, basically, between how to map from the JSON document into the table. Does this look useful? And of course, we have the opposite mappings as well. I just don't have them in the slides. So can you use that yet? So this was introduced in SQL 2016. This is the current standard. It's like yesterday in SQL terms. Yeah, I'm sorry. But you see, there is movement. There is movement. Vendors are taking it up. Anyone using 8.0 MySQL? Anyone wanting to use MySQL 8.0? Yeah, you see? There's a pattern here. So good things are coming to the standard, and vendors take it up more quickly than they used to do. That's I think, the important messaging here. So I see I'm running out of time. That means I desperately need a time machine to go back in time. Of course, everybody wants to have a time machine, and SQL has got a time machine, luckily. Even 2 of them. It has 2 time machines, because 1 is not enough. So time traveling was introduced. And there are actually 2 different ways how time traveling can be done with SQL. The one is called application versioning, and that's intended to reflect how the real world changed. Like, for example, if some people marry and they mail the certificate that the name has changed to their business partners, they will receive it weeks later. And then they will need to be able to say backdated. That name has changed. So application versioning is about modeling how the real world has changed. And on the other side, we have the so-called system versioning, which is modeling how we learned about these changes. Because even if I get the letter from a client today that the name has changed like 3 weeks ago, I might still want to keep track that I just learned about this today. And this is called system versioning, and this is something I would like to demo, or to show you at least. So it is a table-by-table decision. You can, for each table, decide whether to take no versioning at all, like in the past, or do application versioning, or do system versioning, or do both of that by temporal tables. It's upon you, a table-per-table choice. There is some syntax for it. Here's the syntax for the system versioning. So what you need to do is basically you need to add 2 columns which reflect the time frame in which each row was valid. And you're delegating the maintenance of these columns to the database. Generated always as is the keyword here. Then you need a little extra syntax. And then what's happening is you don't take care when you insert into this. You don't touch these 2 columns because you have delegated maintaining these columns to the database. System versioning. The system takes care of it. It will propagate if you run it at 10 o'clock. It will propagate, okay, this was valid from 10 onwards. We don't know how long yet. And here comes the real magic. If you update something, you will end up with 2 physical rows in that table. The old one has been updated to reflect the end time, like 11 o'clock. And the new one then starts at 11 o'clock. And you guess it, if you delete it, the data is not gone. It's still there. It's just marked invalid at 12 o'clock if I run the query at that time. Well, and if you then look into this table, which still has the data, but if you run the query, you don't see the data. Because this feature is designed to be transparent to your application. You don't need to change your application. The only thing the application ever notices is that you have 2 more columns in this table. That's all. It's automagic. But of course, you want to access that data occasionally. So therefore, we have a new distinct syntax in the from clause where you can then basically say, because it's a table per table setup, you can then say, okay, at that table, I would like to look as of that timestamp. And then you will see how that table was looking at that time. Yeah, question?
Is it possible to get like all the range?
Yes. The question is it possible to get a range of timestamps? Yes. You can basically also ask for the full history. Another question.
And the ID is still the primary key?
The ID is still the primary key, yes. The database keeps track of that. This is actually a problem which is way harder for application versioning, but for system versioning, the system just takes care of it. And another question.
And if you add a record at 1 o'clock with the ID 1, do you have a time gap?
Yes, the gap remains there. So till 12 and 1 o'clock, basically the table did not have that key, but later on you can have it again. Okay, any other questions? Oh yes, one more.
So the relation from another table to this record, if another table would reference ID number 1,
Yes.
they would have a reference to number 1 unknown at which time.
So if you, it's about a mixture. I don't know if you're meaning more the join side or the foreign key side. So it's about linking between those tables.
And does the other table have a knowledge of when?
No, the other table doesn't have a knowledge of what time it is, but the query. You can write it into the query. And if you have foreign keys, they are only valid right now, basically, and therefore also in the past automatically. Okay.
How it affects the performance?
How does it affect the performance?
The amount of data would be huge.
No, it depends. So the question is, amount of data might be huge, and how does it affect performance? This is different from vendor to vendor. So there are different ways. So let's go to the slide everybody's waiting for. Lo and behold. Who is using MariaDB? Okay. So the question about performance and size. I think, of course, size, if you keep track of the all data, everything will pile up, basically, so you need to have the space, yes. But it's up to you to which data you use it. If you use it on slowly changing data, like master data, like names of people, then it's not a lot. But of course, yes, it stays there. And when it comes to performance, there are different ways how it is implemented. Like in MariaDB, you can optionally choose to partition these tables in such a way that you have the current records in a distinct partition. And then it's basically like a table was before. Okay, any other questions for system versioning? Yes, you are kind of excited about this feature, I think. Yeah. Okay, I'm sorry, I'm coming to the end. Yeah, I'm running out of time, and even the most exciting time machine cannot help me here. Let's summarize. SQL 92. It was a good standard. It was a round standard, but it's an old standard. A lot has happened since there. Do you see that picture, that pile of paper? That's the printout of the current standard. Not really, because it's only part 2. It has 9 parts. So this part had 1,700 pages, and all 9 together have about 4,000 pages. So this is the current SQL standard. If you think you know SQL, think again. Just to put it into perspective, I don't like those benchmarks like lines of code, but still, pages of specification. It gives you some rough comparison. So we have 4,000 pages today, and with SQL 92, we have had 750 pages. So it's about 5 times as much. And to put it also into context, you have to understand that SQL 92 was mostly focused on the relational idea. And starting from the next run, from 99 on, that relational idea was still there, but it was not a limiting factor anymore. 80% of the current SQL standard are not related to the relational idea anymore. If you think SQL is a relational language, yeah, well, of course, it has its foundation there, and you can still use it that way. But you're only thinking about 20% of SQL. SQL has truly evolved beyond the relational idea. Technically, people are referring to extended interpretation, but I'm more like, okay, I think this is really worth naming another data model, like the SQL data model. It is beyond the relational idea. If somebody's coming up at a project when you suggest, okay, let's use MySQL for that, and somebody's saying, oh no, we need to know MongoDB or whatever, because web scale. And this relational database, these dinosaurs, they cannot handle that. Then you should answer, no worries. We are not using a purely relational database. We are using an SQL database. We can use it in a purely relational way, but we can also create a single table with a single column, JSON. You can put a check constraint there if you want to have an underscore ID member in each element you're putting in there. And this is what basically MongoDB is. You can implement it in like one create statement in any SQL database. It's really beyond the relational idea. And last but not least, CRUD operations. Create, read, insert, delete, the life cycle of each entity. If you're using SQL only to do these basic CRUD operations, mostly by ID, by primary key, then you're not actually using SQL. The idea behind SQL is the transformative power to have the persisted, non-moving data model, which is only there to accommodate the data, which moves slowly compared to the requirements, what you want to do with that data. And the powerful transformation language to transform that on the fly for all the different requirements that are popping up from marketing to sales to whatever. This is SQL. It is the transformation language for things like JSON table, as simple you have seen it there. So what's remaining? You need to learn about it. No question. You should learn about it. And that's the reason why I write on modernsql.com. That's my website. I'm writing basically a book about this thing, but while I'm writing it, I'm publishing it there for free. So it's early access if you want to say so. Just subscribe the blog, follow the Twitter handle, and learn about these things, because they can make you a more productive developer. That's what I truly think. And last but not least, if you want training, winand.at is my website. There you can find some offerings. You should also grab some coasters and stickers there, no question. Just come up here, take what you want. My name is Markus Winand. I'm the SQL Renaissance Ambassador. If you have any questions, just reach out for me in the break, because now we have only one more important thing to do than learning SQL. Ice cream.